Hey, I'm back. What have I been doing? Well, I've been working on this video. This is the third iteration of this video. If you are new here, because I've gotten some new subscribers over time, it's probably mostly thanks to Too Mad, but then again, I did pay him. But credits due where credits due. And if you're new and you just haven't subscribed, I would very much appreciate it if you did. Alright, so as referenced in the title, I'm working with an autoencoder. So an autoencoder is basically a neural network that compresses data and tries to be as lossless as possible. Lossless, in this case, in the image reference, meaning as close to visually no difference as possible. Now, I'm not going to explain neural networks in this video because that is a vast topic. It took me 7 years to figure out how to do it. Jeff Hinton's Neural Networks playlist is going to be in the description if you want to watch how to make that. But for now, all you need to know is a neural network is basically just a program that tries to emulate the way that the human brain learns. Okay, image compression. Why can't you just zip it? Doesn't that give like a good enough result for compression? Well, zip or tar or whatever you're using, that uses a generalistic algorithm to compress, which means that it can compress any file type. It does it down to the binary level. It does this by trying to find patterns and things that are the same and just, crunch the numbers down. But for an autoencoder, you can get very, very small file sizes and huge compressions compared to zip. Okay, well, what's the difference between an autoencoder and a zip file? Well, an autoencoder trains on your training set. This training set is what you're expecting to be zipping. And if you know neural networks enough, you know that you need an error vector or an error function to tell it how well it's doing. Well, for an autoencoder, your input, let's say you have a 64 by 64 resolution image. You compress that into a vector, which is 4096 by 1, and a vector is just a long string of numbers. This means that we have 4096 inputs as well as 4096 outputs because we're trying to get the same image out. Whatever your neural network outputs, you can just give an error function of the same input vector because you're trying to expect the same thing out. Alright, so how does compressing work if it just gives you the same thing out? Isn't that just giving the same image? Well, no, not necessarily. The idea is you split the neural network in half, and now you have an encoder, which is the big to small, and you have a decoder, which is the small to big. The middle layer of an autoencoder is usually called the latent layer. It's what has all the values that it's stored for encoding, and that is what you save. For this project, I have 10 values of latent space, but because of this, I'm definitely overfitting. It has worked on the training set, but the problem is, it's not general. It only works on the training set. If you go outside of the training set, you get demon images. Alright, so cool. What's the process behind this? Well, I've got a whole bunch of images, 531 to be exact, from my yearbook. And I've gone through the liberty of taking that yearbook in every single page and scanning it. So then I wrote a program that makes it really easy to save images of people's faces. And now that we've split all the faces out, the problem is they're not the right size. See, I don't have the 3090 yet, I'm waiting on that, but I only have 8 gigs of VRAM right now. And images on 256 by 256 resolution takes a lot of VRAM. But do not fret, I have made a program in processing that takes images and resizes them. Also, there's not going to be any color because I did not have enough VRAM to train for RGB. It's all black and white. Alright, so our images are resized, they're all the same resolution. Now we can convert them to a NumPy array. I'm going to be using NumPy arrays because I need those image pixel values, which are numbers, into number arrays. And it's almost always easier to store image pixel datas as vectors or tensors if it's in your GPU, rather than just storing the whole image. Your GPU does this anyway. So I built a Python script to convert these images into a NumPy array. So now we need to start training, and that is where the problems happen. For a long time I ran out of VRAM. I got a lot of errors, but for now we're gonna have to live with 64 by 64 resolution, black and white. So to start training, well, I've compared 15 and 10, and as you can see, the difference is actually quite drastic, but the problem is the algorithm that I use for error checking is really lenient on things that are wrong. Okay, so why is there such a difference between 15 and 10? Well, the problem is the error formula. And when we look at the square of x, when you sum things up, they get really big really quickly. And this is why the accuracy looks way better even though nothing has changed. Alright, so what's next? Well, we have to split that neural network down into an encoder and a decoder. These are two separate neural networks. So what can we do now? Well, we can take many faces and we can just encode them all. And if we were trying to compress them, we could save those latent values. And this would be the difference between 74.3 megabytes and 5.31 kilobytes. That is more than 130,000 times smaller. But because the latent values are so small, overfitting. You can't add any more, or else you're gonna have to train it again. But for this, I have a better idea. You see, we get latent values out, but if we linearly interpolate each one, we can morph a face from one to another. All right, so let's see that. Alright, that's pretty cool. It's trippy, but hey, pretty cool. Alright, well, I keep talking about overfitting. What if I was to add a new image, something that's never seen before? Like an alpaca. For instance, alpaca, whatever. Alright, so I go through the same conversion process. I convert it to a NumPy array through my converter, and I bring it into the encoder. Now I have a latent value. When you bring this into the decoder, it looks like a nightmare. This is because it's never seen it before, and my neural network's overfit. It's only fit to the training data I've given it. This is normally not good for any neural network. You want to train it less if it's overfitting, so it's more general. But for this, I don't actually care. Alright, that's pretty cool. What if I take another image that's similar, like another yearbook photo? Maybe not from the same school, but maybe it'll work. Alright. Well, it looks better than the alpaca. It's not like I could compress that. Well, that's all I really had planned. I mean, you can do so many other things with an autoencoder. You can do so many other things, I'm sure, with this project. Of course, I'm going to be working on more projects, but that'll be a little while from now. I'm currently working on a game. I'm currently working on like 27 YouTube videos, and I'm working on a whole entire project for my wall. Nevertheless, I hope you guys like these videos, and I hope you guys subscribe. It just helps me out. But for now, I'll let you get back to whatever the hell you're doing before. But that's all I really intended to show.